Hello and welcome back to another electronic circuit review. Before we analyze this precision rectifier, let's have a quick overview on how an operational amplifier works. You can skip this part if you are already familiar with the op-amp basic functions. Consider this operational amplifier with two inputs, V plus and V minus. And one output called VO. This op-amp supplied by positive and negative voltages. Now let's assume V plus is greater than V minus. Then the output voltage VO will swing to positive high, because op-amp will multiply this voltage difference between V plus and V minus by its high circuit gain, which is in order of 1000 to millions. So for any positive differences, even very small, the output will swing to its highest positive voltage, which is close to the op-amp power supply. Now assume V minus is greater than V plus. Then the output VO will swing to negative low, and again this is because op-amp will multiply this negative difference by its high circuit gain. The output high and output low voltage values are dependent on the op-amp positive and negative supply voltages. In general, an op-amp output can almost swing to its power supply voltages. In case of a single polarity power supply voltage, positive and ground, the op-amp output can swing between positive power supply and the ground level, which is 0 volt. A quick reminder on virtual shorts principle. For feedback amplifiers constructed using op-amps, the V plus and V minus input terminals will always be approximately equal. So we assume the input terminals are shorted together. Now back to analyzing this precision rectifier. Let's assume Vi is positive. Then since Vi is connected to V plus of the op-amp number 1, then output of this op-amp will swing to its positive high and turning on the diode D1, which this creates a negative feedback path for op-amp number 1. Now by applying the virtual short principle, we will have Vi at V minus terminal of the op-amp number 1 and directly to the output VO. At the same time, with a closer look at the op-amp number 2, we can see that the Vi is connected to the V minus terminal. So this results output of op-amp number 2 to swing negative low, turning the diode number 2 off, and this stops the op-amp number 2 affecting to the output VO. Just op-amp number 1 is operating here. Before we continue, please subscribe to the channel if you haven't yet. Your support will help this channel to grow and encourage me to create more content. Thank you, and now back to the video. Now assume Vi is negative. Then since the V plus terminal of the op-amp number 1 is connected to Vi, this will result output of op-amp number 1 swing negative low and also turn off the diode number 1. So no negative feedback path for op-amp number 1 in this case, and therefore it won't affect or contribute to the output VO. This will remain off. However, the output of op-amp number 2 will swing to positive high because its V plus terminal is grounded, and its V minus terminal is connected to Vi by R1. So since Vi is negative, then V plus is greater than V minus, and this is why op-amp number 2 will swing to positive high. This will turn on the diode D2 and creates a feedback path for its output to its V minus terminal through the R2 and to Vi through R1. As you probably noticed, this will create an inverting op-amp configuration with a gain of negative R2 over R1. So with a negative Vi, the output Vo will be equal to minus R2 over R1 multiplied by Vi. And since in this example the R1 is equal to R2, then we will have a positive Vi at output Vo. And Vi by itself is already negative as we are here. Let's draw the output voltage. As you can see here, this circuit rectifies the input signal with the ability to change the output voltage amplitude for negative inputs. This op-amp circuit called a Precision Full Wave Rectifier. If you enjoyed watching this video and found this channel helpful, please like, subscribe, and share your thoughts under the comments.